viewers, I'll be looking at conductors and currents in this particular lecture. Conductors and currents. First and foremost, what are conductors? What are conductors? Conductors are materials. They are simply materials that can conduct electricity. Either we say they are materials that can conduct electricity, or we can simply say they are materials that allow electric current to flow through them. We have some few examples that we'll take. Examples are, we have silver, we have aluminium, we also have copper. These materials, they are very good for conduction of electricity. Now, before we talk about current, we're going to look at a concept called charge. Charge. What is charge? Charge is simply a property. This is a property exhibited by particles in the presence of an electric field or a magnetic field. So the behavior a particle exhibits when you bring it close to a magnetic field or an electric field is simply described by charge, or simply described as charge. Without going further on that, we'll define current based on this charge, because for you to talk about current, it implies that there must be movement of these charges from one point to another. So assuming we have a conductor with a cross-sectional area A, if charge, let the charge be equal to Q. The area of the cross-sectional area of the conductor is equal to A. Now, the net flow of this charge across an area in a time interval delta t is referred to as the current, the average current. So we can define current I as the charge flowing per unit area, the charge flowing across a cross-sectional area per unit time. The charge flowing across an area per unit time. So we say current equal to charge flowing across an area per unit time. The SI unit of current is the ampere. I can take this off. Let me wipe this, then we'll continue from there. So like I said, the SI unit for current SI unit for current is the ampere, abbreviated by capital letter A. So if we say that current I is equal to charge all over time, the SI unit for current is ampere, that of charge is coulomb, and that of time is a second. So we can say that from that equation, 1 ampere is equivalent to what? 1 coulomb over 1 second. So we can say that an ampere is equivalent to 1 coulomb per second. Of course, we have smaller currents that may be expressed in terms of milliamperes. Say milliamperes. Milliamperes is equivalent to 10 raised to power minus 3 ampere. So we say 1 milliampere is equal to 10 raised to power minus 3 ampere. You also have microamperes. Microamperes. That is equivalent to 10 raised to power minus 6 ampere. So we can say that 1 microampere is equal to 10 raised to power minus 6 ampere. So let us look at the magnitude of current in a conductor. If I have a conductor, cross-sectional area A, have a conductor with cross-sectional area A. We know the number of charges, number of mobile charge carriers flowing per unit volume. We have the cross-sectional area. We know the velocity with which these charge carriers move and the charge on each particle. We can, based on these parameters, find the magnitude of the current flowing in that conductor. So if we have, let's say this is a conductor, let's just use a simple figure. This is a conductor. So mind you, the topic here is magnitude of current in a conductor. So assuming this is a conductor and you have the cross-sectional area as A, these are the charges, okay? You have charge, and they are moving with a velocity called the drift velocity. Moving with a drift velocity. Now, the magnitude of current in this conductor we can express it as I is equal to N A Q V subscript D. Here, N is the number of mobile charge carriers. A is the cross-sectional area, or just say simply area. cross-sectional area of the conductor. Q is equal to charge on each of the particles. While V subscript D is drift velocity. Is the drift velocity. Now in some textbooks or in some conventions, you may see, instead of you seeing Q, it may be represented by E. E is electronic charge, so it is still the same thing. So in that respect, we can rearrange or rewrite the equation for the magnitude of current in a conductor as I is equal to N A E V D. E is the same thing as Q, which is equal to charge. So either way you can find the magnitude of current in a conductor with that formula. Then we also look at a concept called the current density. Current density. What is current density? It is simply the current flowing per unit area. It's simply the current flowing per unit area. I can represent current density as J equal to I over A. And if we recall that I is equal to NAQVD, we can then say J is equal to NAQVD all over A. Is cancels out and you are left with current density as NQV subscript D. So I'm going to take this off. Then let's look at, and just as a means of moving forward, if we maintain a potential difference across a conductor, what happens is that an electric field and a current density can be established in the conductor. And in that case, the current density is somehow proportional to the electric field in some material. So we can also express current density in terms of the conductivity of the material. And so that gives us J is equal to conductivity times the electric field. Electric field. Then let us look at Ohm's law briefly. Okay, before we look at Ohm's law, let us take a little problem. A little problem on finding the magnitude of current in a conductor. Assuming I have a material, maybe a conductor, where the free electron density, you say free electron density if you use free electron density of 10 raised to the power 24 electron per second, this is the same thing as saying number of mobile charge carriers. Okay, assuming you have a drip velocity, maybe voltage is applied and you now have a velocity of about let's say our velocity is 1.5 times 10 to the power minus 2 meter per second. If the cross-sectional area, let's say the area of the material is 1 centimeter squared, electronic charge Q, electronic charge is given as 1.6 times 10 to the power minus 19 coulomb. What will be I? You can use this formula to calculate the value of I, as I is equal to NAQVD. But if you check this problem, you discover that the area is in centimeter. It has to be converted to meter squared. Area is in centimeter squared. So we have to convert it to meter squared. How do we do that? Let's proceed in the other section. So I have to wipe these parts. Now, if the area is 1 centimeter squared and we want to convert to meter squared, how are we going to do that? It's quite easy, but a little bit confusing to young undergraduate learners. So remember that 100 centimeter is equivalent to 1 meter. So if we divide this by 100, divide both sides by 100 to obtain 1 centimeter, we then have that 1 cm is equal to what now? 0.01 meters. So 1 centimeter squared will be equal to 0.01 meter all squared. If you do this, this will give you 10 raised to the power minus 4 meter squared. So we have been able to convert to meter squared. So we then come back to our expression by saying I is equal to N is 10 raised to the power 24 times A is 10 raised to the power minus 4 times our Q is 1.6 times 10 to the power minus 19. I'm just excluding the units because they are all in SI units. Then V subscript D was given as 1.5 times 10 raised to the power minus 2 meter per second. So if you do your mathematics very well, your current will give you 0.24 ampere. That is the answer to this particular problem. There are other problems you can also handle. If you are solving, for example, if you come across a problem where you are told about the mean velocity of electron flow, if you come across any problem of such, what they mean is just simply the drift velocity. So without even expressing it, saying drift velocity, if we say the velocity of the mean electron flow, it is still the same thing as your drift velocity. So there's no big deal about that. So once you come across any problem that requires you to find, let's say for example, the drift velocity when other parameters are given, you can use this particular equation. This is, let's say, recall that I is equal to NA QV subscript D. Assuming the question requires you to find the drift velocity or the mean velocity of electron flow, all you needed to do was to express the drift velocity as a function of that equation, as in express the drift velocity as the subject of that expression, so that your drift velocity will now be current I all over N A Q. So this is all for conductors and currents. We'll look at resistors, potential difference, Ohm's law in our next lecture. We'll have a nice time.